Thank you very much for the invitation. A pleasure to be here. So I wanted to share some of our recent work, but it took several years to develop, to finally crystallize it in its present form. And it has its origins in some work that began more than 10 years ago with several colleagues from the Physics Institute back in Mexico City. So we began studying rank dynamics. We were first using rankings of the Google Ngrams dataset, so the words in different languages, they can be ranked and you get a distribution which is known as Zipf's law, because George Zipf described it in the 1930s, and when the distribution had been described already in the late 19th century. But let's say we had enough data so that we could study how these distributions change in time. And we explored many things. And a couple of years ago, we published a paper in Nature Communications where we, let's say, after analyzing dozens of different data sets, where we had enough data to study how rankings change in time, we found some universalities, and we explained why these type of dynamics are universal. But even before that, we were wondering why, let's say, in languages or in sports or in Fortune 500 companies or in city population, I mean, all these different data sets where you can get rankings and then this ranking change in time, we were finding similar dynamics, or like in this image, rankings of universities. Roughly speaking, in all of this, you have the low ranks. In other words, the most relevant elements changing slower than the least relevant elements. And our hypothesis was that this was useful for evolution, because at the same time, you could have in a system robustness and adaptability, which you want, let's say, the essential features of a system to be preserved so that its function is maintained, but you also want some adaptability. And it makes sense that the least relevant elements are the ones that change, so that, let's say, you can explore at the same time that you maintain the most relevant features of your system. And I mean, this has been studied thoroughly in complex systems, and it's related to criticality that I will mention in a moment. But let's say, it seems that when we had this temporal heterogeneity, we were getting for free this, at the same time, robustness and adaptability that you find in criticality. But I mean, I will go more into it. So we wanted to study different types of heterogeneity, which is basically when you have a diversity of elements. It's usually easier and simpler and convenient to model systems as homogeneous, because then you can treat all elements as the same, and then you can make several simplifications. However, it's actually easier for nature to have heterogeneity than to impose some mechanisms that will ensure homogeneity. And an example you can see in synchronization, that it's easier not to have synchronization than to have synchronization. And synchronization would be an example of homogeneity, temporal homogeneity. And if you have different elements with their own frequency, then you have heterogeneity. But of course, mathematically, it's easier to speak about homogeneity. But let's say we have powerful computers, so we can study heterogeneity, and we have enough data to try to match this with real phenomena. So I briefly mentioned three types of heterogeneity that we studied. So structural heterogeneity, which has to do with topology and has been studied thoroughly with network science. And one example is the commercial air travel network. So you have airports as nodes, and then you link the airports if there are flights between them, and then the size of the nodes, it's how many flights they have to different destinations. And of course, there are some big airports like LA, San Francisco. This one might be Denver. I don't know, Atlanta. In Europe, probably London, Paris, Amsterdam, Frankfurt, and so on. And these topologies have been studied thoroughly, and they are more or less scale-free. I mean, in some cases, not precisely scale-free, but in general, you have few elements with lots of connections and most elements with not so many connections. And this has advantages because you can have an increased variety. If you have this diversity of elements, you can have, let's say, if you have systems that have functions at multiple scales, then you can have an increased variety, and this is related to Ashby's law of requisite variety, which was proposed in cybernetics, which tells that if you want a controller, it requires at least the same variety as that which is trying to control. And this applies to machines and to animals. So imagine if you want a robot in a factory to distinguish between 5 different situations, then it needs to have the variety of those 5 different situations. So it's variety is simply the number of states a system can be in. So of course, there are different mechanisms that will produce structural heterogeneity. And I mean, this has been studied thoroughly. And temporal heterogeneity has also been studied. I mean, there are plenty of examples like solar flares. They're also known as bursty dynamics. So human communications follow this pattern, like texts or phone calls or internet visits or usage of money. Brain activity is also following this pattern. Epidemics, wars, and also it seems that maybe mass extinctions have these distributions. Earthquakes, foraging in different animals. And the advantages of having different temporal scales are similar to the advantages of having different spatial scales or structural scales, in the sense that you can have an increased variety and systems can adapt at all those multiple scales, which is useful if you don't know at which scale you need to respond, let's say, if there's a perturbation. And finally, we also studied functional heterogeneity, which has also been studied thoroughly because it's everywhere, but because it's everywhere, it's not named as such. So, I mean, here's an image of the Seven Samurai, and I mean, could be an Avengers film or Ocean's 11. So imagine a film where all the characters have the same abilities. It would be pretty boring because like everybody does the same. So you need to have like the smart guy and the strong guy and the, I don't know, the funny guy, and they all have different abilities, and then that makes the film entertaining. And at the same time, they're able to solve whatever challenge they're facing. Armageddon would be another example, no? So if you have different elements in a system that are better for different functions, then the variety of the system will be greater than if all have the same function. But of course, if you have a homogeneous system, then your system will be more robust, because if, let's say, one of the elements fails for whatever reason or is destroyed, then the other elements can maintain the function of the system. So if, let's say, depending on how many elements and how much they cost, if our system requires a high variety, it's better to have heterogeneity. And if the system requires a low variety, then it's better to have homogeneity. And in most cases, just a balance between those two extremes. But let's say in many different disciplines, this has been studied in terms of specialization or division of labor, also the study of cooperation, coordination, and communication. They'll have to do with functional heterogeneity. In a sense, if you have heterogeneity, that may imply that you have less competition, so it can favor cooperation. And for example, in sport teams, you usually have heterogeneity. So in soccer, let's say you can have the best goal scorer, but if you don't have good midfielders, then the goal scorer will never get the ball. So of course you need heterogeneity of good players in different positions in order to have a good team, and of course also that they are coordinated properly. And if you had like a sports team, let's stay with soccer, where all the players have the same ability, then very probably it would be a very lousy sports team, because let's say, of course, you could make changes and you could maintain the same level of the team, but then let's say you will have like a very good scorer or a very good goalkeeper or a very good defender and so on. So in a sense, if you have heterogeneity, you can do more with the same number of elements. But if you have a repetitive task, mainly lower variety, then you don't really need that increased variety. So then homogeneity would be maybe cheaper, and also it might be easier to coordinate homogeneous elements and heterogeneous elements. So yeah, it's a balance between redundancy, where you have all the elements being the same, and variety, where each element is different. So if you imagine a fight between two armies, one where all the soldiers are exactly the same, and another army where all the soldiers are completely different and there's no overlap in their functionality, who would win? And I mean, I think either case, it's not desirable. So say some balance between extreme heterogeneity and homogeneity would be best. And of course, the question is what would be the best balance. But so we wanted to study what was the effect of having or not having all these three heterogeneities: structural, functional, and temporal. And we use random Boolean networks. And also we use the Ising model, but I'll not present those results, but basically the same conclusions hold. So let me briefly tell you about random Boolean networks in case you're not familiar with them. They were proposed by Stuart Kauffman in 1969 as models of genetic regulatory networks. So you have nodes which represent genes, which can be on or off. So they're Boolean variables. And then they're linked to k other genes that basically will determine what will be the future states of those genes. So, I mean, back in 69, we had no idea how many genes any species had. There was this idea from Jacob and Monod that there were genetic regulatory networks from the early 60s. We had no idea what kind of topology they had. So what Stu did was to generate random networks. So it's like, okay, we don't know which kind of network, so just let's just explore the space of all possible networks and see in that space of parameters which ones have the properties required for life. So he basically generated ensembles of random networks with different parameters and then studied their statistical properties. So a network has n Boolean nodes with k inputs in the classic version, because there are many variations. And then we have lookup tables that determine what will be the future state of each node. So each node has its own lookup table. And we generate a random topology if we don't have data, because of course, more recently, now we have data about real genetic regulatory networks, and then we can build realistic models. Well, let's say with the same principles. But let's say before and still now, we can just generate the connections randomly and also the lookup tables. So this would be an example of a lookup table. So if we just focus on node O, it has as inputs nodes N and P. So depending on the states of N and P, the state of O will change in the next time step. So this lookup table considers all possible combinations between N and P in time t, and then at time t plus 1, I mean, this would be what XNOR function, but basically you generate this randomly with a bias P, and that P would be the probability of having ones in this column of the lookup table. If P is 0, then you have only zeros, and then it's a very boring function. If P is 1, it's only 1, so it's also boring. So if P equals 0.5, we say that there's no bias, so you have the same probability of zeros and ones in lookup table, so that gives you like the most complex dynamics. So here it's just the dynamics of a randomly generated network. I don't know, maybe with k equals 2. And you start with random initial conditions, and then after some transitions, you find that there's a repeating pattern. Each column would be a different time step or a different state of the network. And each row here would be a different node as it evolves in time. And one color would be on and another color would be off. The topology and the lookup tables, let's say the structure and the function define the state space. So we have n nodes, but then the state space is 2 to the n nodes, each node of n bits. So now these letters represent states of the whole network. And once you repeat a state, you say you fall in an attractor, because these are deterministic systems. Well, this flavor of random networks are deterministic, and they're also dissipative. So let's say once you repeat a state, you know you are in an attractor, and then all the states leading to that attractor are called the attractor basins. And so you have some states which are called cardinal hidden states, because you can only reach them from initial conditions. And then states can have multiple predecessors, but they have only one successor. So the question on the relationship between the topological network and the state networks, it's similar to what's the relationship between structure and function. So it's what's the relationship between making changes here or here, which changes will make in the state space. And that's like a open question, but with this type of models, you can explore in a systematic way. And there are 3 different dynamical regimes. So for P equals 0.5, meaning when there's no bias in the lookup tables, you will have a phase transition between order and chaos at k equals 2. If you have few connections, you have order dynamics that are very robust. Most nodes don't change, and you have convergence to similar states. So if you make a mutation somewhere here, very probably the network will return to its attractor. When you have lots of connections between nodes, you have chaotic dynamics. So the randomness, most nodes are changing. You have fragile dynamics. You have divergence of similar states, meaning that if there's a small perturbation, and then you will continue the trajectory of that state, it very quickly would diverge, meaning that the states would be very different. And then close to the phase transition, we have a third regime, which is called critical, where there's a balance between order and chaos. So you have some static nodes, some changing nodes, some changes spread locally. So let's say it's rare that you will have avalanches that spread all over through the network. And in this region of the parameters, you have maximization of information storage, of coherent information transfer, of Fisher information, and let's say many other nice properties. So in the late 80s, early 90s, actually, right now I'm in Santa Fe Institute, so precisely here, people like Chris Langton and Stuart Kaufman argued that life and computation had to exist close to the so-called age of chaos, which was how they called back then criticality. Now people usually don't use that name. In the sense that if you have order dynamics, then you have robustness, but then you can't adapt. And if you have chaos, then in principle, you can have adaptation, but then probably if you already had some good solutions, you will lose them because there's too much change. So somewhere in between, there's, let's say, this Goldilocks region where you have enough robustness and enough adaptability so that life can emerge. And much later, I mean, less than 15 years ago, when there was already enough data from real genetic regulatory networks, then they analyzed them, and it turns out that they are either critical or close to critical, but let's say on the order side, and I'll mention why they are on the order side. So let's say when you have networks that have these properties, then you can have a balance between robustness and information storage and variability and computation and exploration, which basically is necessary for evolution. And then there have been other works that explore how could evolution reach this type of networks, and there are many different studies. But the thing is that people were trying to, well, makes sense that we want critical dynamics for these reasons, that you have this balance between robustness and adaptability. But then the parameter region where you have critical dynamics is very narrow. So the question is like, okay, from all possible networks, very few are actually critical. How could evolution find those precise critical networks, the precise parameters that give you that criticality? So in these models, we introduce heterogeneity. So for structural heterogeneity, we compare exponential distributions versus Poisson distributions. And I mean, Poisson distributions are not homogeneous, but let's say they're more homogeneous than exponential. For temporal heterogeneity, back in my master's, I proposed deterministic asynchronous updating. So basically, different nodes update at different speeds. So basically, we see how many outputs a node has, and then that number would be its period. So if I have 1 or 0 outputs, I will update every time step. And if I have 10 outputs, I will update only every 10 time steps. And so the more connected, well, the nodes with the greatest inference will be the slowest, which is what we observed in our rank dynamics work, that the most influential or relevant elements change slower. And then for functional heterogeneity, we play with this parameter P, which is the probability of having ones in the lookup table. So instead of having all nodes, let's say, to generate the lookup tables of all nodes with P equals 0.5, we have I believe it's a Poisson distribution with mean 0.5. So some nodes actually will have a bit lower than 0.5, and some will have a bit higher than 0.5. Or maybe it's a Gaussian distribution, I forget. So in these results, we plot the complexity. I will speak how we get this measure of complexity, but it's basically a proxy for criticality for different combinations of homogeneity and heterogeneity of networks of size 100. So let's say the classic all homogeneous networks is the green curve. So the phase transition is precisely where the complexity is maximum, which would be critical dynamics. And let's say to the left it's order region, to the right it's chaotic region. So we see that as we add heterogeneity, so for example, this one is structural heterogeneity, then the curve shifts to the right, but the area where you have high complexity, it's much higher. And then if we add 2 types of heterogeneity, so let's say that this would be only functional heterogeneity, this one only temporal heterogeneity, which shifts to the right, but let's say that's the only case where the area is not greater. But then if you add 2 types of heterogeneity, then shifts even more to the right, and then the area extends even more. And if you have all 3 heterogeneities, the black curve, and basically you have, for majority of networks, you have critical dynamics. So what we say is that the heterogeneity extends criticality, because now instead of having a very narrow area of the parameter space where you have critical dynamics, now most of the parameter space has critical dynamics. This is just an example of k equals 10 to see how this type of dynamics look like with high complexity. And it extends not only criticality, but also antifragility. So let me quickly explain what's antifragility. So this was proposed by Nassim Taleb just 10 years ago in his book Antifragile. And it's basically the property of systems that benefit from noise or perturbations. So imagine that you have some fragile thing like, I don't know, some crystal cups that you want to send by post. Then you put a label that says, do not mishandle. This is fragile. Why? Because if you shake it, it will break. So a fragile system, it's one in which perturbations destroy the function of the system or degrade the function of the system. So you don't want that. And then you make everything possible to, let's say you build buffers or you try to protect the system from perturbations because it's fragile. If you have a robust system, let's say if you have rocks or logs and you send them by post, then you don't put anything because you don't care if they are perturbed or mishandled. So a robust system is one in which the function does not change in face of perturbations. But then if you have some anti-fragile system, then and you send it by post, then you put a label that says, please shake, because when it reaches the destination, it will be in better condition than if you don't shake it. So that's an example of a system that benefits from perturbations. And initially, it might seem counterintuitive, but I'm from Mexico, so we have in Mexico aguas frescas, which is basically water with fruit pulp and sugar, and especially the tamarind water, it very quickly settles in the bottom. So in order for it to taste good, you need to shake it, you need to stir it so that it kind of mixes a bit, and then you drink it, and then it's tasty. If you don't shake it, it's first it tastes only of water, and then at the end you get all the pulp, and then it's not nice. So aguas frescas are antifragile, but I mean the immune system is antifragile. Sport, it's another example of antifragility in the sense that our bodies increase our oxygen consumption, which in theory should accelerate aging of our cells because there's more oxygen. So then they should oxidize faster, but then our body generates antioxidants which overcompensate the increased oxygen. So the total effect is rejuvenating. But of course, if you run a marathon a day, probably you'll age faster than if you don't do anything. And more generally, hormesis will be an example of antifragility. But of course, there's always a point where too much noise starts degrading the system. So we propose a measure of antifragility, which is, well, actually, this is a measure of fragility. And we basically measure the perturbation, which would be delta X, or let's say the effect of the perturbation in the system, how much the system changes. And delta sigma would be change in satisfaction. And this satisfaction, it's very arbitrary. So whatever we want the system to do, that's, if it's if it's functioning well, that's high satisfaction. If it's not doing what we want the system to do, then it's low satisfaction. So if the perturbation improves the function of the system, then it's antifragile. That's basically what this measure represents. Taleb proposed a different measure of antifragility, but nobody I know understands it, so we just proposed our own. And we have used this in many different contexts, in ecosystems and in cryptocurrencies and stock market and here with random Euler network. So we can just focus on the left side of this figure. So as we increase the perturbations, we see for networks of different connectivity, how their fragility changes. So this would be all homogeneous, topology, temporality, and function. This would be all heterogeneous. So instead of just presenting all 8 cases, I'm just showing you the extremes. So it would be the green curve and the black curve. And so for homogeneous networks, let's say you have antifragility for k equals 1, and for k equals 2 just a bit, but then for k equals 3, it's already fragile. So basically, dx means how many nodes will be perturbed every time step. And then the satisfaction is basically the complexity, because we want the networks to have complex dynamics. And then, of course, if you have a high K, you already start, I mean, you don't need perturbations to have complex dynamics. You just, let's say, increase your change or your chaos and your fragility. So if you have heterogeneity, you will have antifragility for networks of K all the way to 4, which, let's say, in this case are already chaotic, but here they are slightly antifragile. And then with K equals 1, they will be antifragile still for X equals 100. So you can be perturbing like all nodes constantly, and it still will be slightly antifragile in the sense that it will be close to, with this amount of noise. Basically, if these curves are negative, let's say below this 0 dotted line, it means that the perturbations will take it closer to criticality, or let's say to the phase transition. However, if we want maximal antifragility, then the homogeneous case will be best, because let's say this is the K equals 1 with all homogeneous. That gives you maximum antifragility. Let's say this would be broader, but this would be deeper. So it's like also depends what kind of antifragility you want. And then, I mean, when we were working on this, we were thinking, okay, let's come up maybe with some other examples. We did the Ising model, we got very similar results. But instead of just, say, doing, I don't know, heterogeneous prisoner's dilemma, heterogeneous game of life, I don't know, whatever model you would like, heterogeneous neural networks, we just thought, okay, let's not measure the complexity of all these different systems. Let's just measure the distributions of, over this function of complexity. So this measure we proposed about 10 years ago based on Shannon information. So basically, Shannon information is correlates with change. So the more change you have, the higher this information is, and then you just normalize it to interval 0, 1. So this, well, let's say if you have a random string, then that will have maximum information. If you have a regular string, let's say only zeros or only ones, that will have minimum information. So the probability of having ones in a string, it's here on the x-axis. So this would be Shannon information. It's maximum on 0.5. It's the same probability of having zeros or ones. If you generalize it, I mean, Shannon information is basically a measure of the homogeneity of a probability distribution. If it's completely homogeneous, if you have the same probability of having any symbol in your distribution, then you have maximum information. If you have probability of one of having only one symbol, then you have zero information. And then let's say we're interested about measuring emergence and self-organization. This is a longer story and might need further justification, but basically we define complexity as a balance between emergence and self-organization. And self-organization, it's like 1 minus entropy, which is information, because organization is precisely the opposite of what I mentioned. If you're interested, I can explain why later, but if not, then you can just believe me. And then complexity is just the balance between these two, which if you know the logistic function, you might ask, okay, why does this have the shape of the logistic map with a parameter that would give you maximum chaos? I have no idea, but let's say it seems it had to do with some operational principle. But yeah, it's the same equation. So let's say this red function would be function of complexity. So instead of measuring what complexity values we will get with some model, and then it's heterogeneous version, we just thought, okay, what would be the complexity of distributions, of different distributions? So it's like, okay, we'll just generate different distributions and then we'll just measure the complexity. So let's say the blue dots would be homogeneous cases where basically all the elements have the same probability of having one-cylinder strings. So it follows the same complexity curve. And then this will be heterogeneous distribution. So basically, we generate distributions with a certain mean, and this is, let's say, where we draw the triangles. And then we see that it has intermediate. So basically, when the homogeneous case is lower than half, then heterogeneous is better, and vice versa. Why? Because let's say if you have here, let's say, let me go back here, maybe it's clear. So if we focus just on the red curve, if we have a distribution of points somewhere here, then let's say we will get some higher points of complexity somewhere here. But if all the elements have the same value, then we will have very low complexity. So let's say if in the distribution the average is greater than the mean, then you'll be able to have a greater complexity. But then we generalize because, let's say, we thought, well, maybe not everybody likes this measure of complexity, so we'll just look at any function when heterogeneity gives you a higher value than homogeneity. And we can get this with Jensen's inequality. So if we just have a function, whatever function that we are trying to maximize or minimize, then we just flip what I'm about to say. And the homogeneous case would be when you have a value and other elements have that value. And then the function of that value will be the function, let's say, of the system, because all the elements have the same value. So for the homogeneous case, the function of the mean, let's say you get the function of the mean because all the elements have the same value. But then if you have a heterogeneous distribution, then each of the elements will have a different function, and then you have a distribution of the function of the elements. So if the mean of the functions is greater than the function of the means, then heterogeneity is better than homogeneity. And we know from Jensen's inequality that this is the case for any convex function. And if it's concave, then homogeneity will give you greater values than heterogeneity. And if it's a linear function, then we don't care because they give you the same value. So that's like a very general way of deciding a priori when heterogeneity is better than homogeneity. And we have applied this already to a few cases, particularly in search, to genetic algorithms, to the traveler salesman problem. Here I just showed the n-queens problem, which is this chess problem where you have n queens. So how many we have here? 8 queens in a 8x8 board. And then you need to find the positions so that no queen is attacking any other queen. But of course, you can increase the size of the board, which equals the number of queens. So let's say this for 500 queens in a 500 by 500 board. And let's say with temporal heterogeneity, you get faster and better solutions, about 10%. But then the question that we're interested in is, okay, how could we find optimal heterogeneity? Because, okay, if we see that heterogeneity in many cases is beneficial, but then we could have more or less heterogeneity, what would be the optimal heterogeneity? And because of the no-Lorentz theorem, or probably this depends on the problem. Well, actually, we already have some results that show that there is no single optimal heterogeneity. It does depend on the problem, but we want to analyze systematically some general scenarios, because probably we will be able to say something about, let's say, what type of heterogeneity would be useful to start with for different situations. And of course, in the examples I have shown, I don't consider cost, because, for example, for random Mooreland networks, we get greater complexity for more heterogeneity, but this also implies more connectivity. And then if connectivity is expensive, then you might not want such greater complexity or criticality, because you want to save on the number of connections. I mean, that's just another factor that right now we did not consider. And another open question is, how heterogeneity has played a role in evolution. I mean, how heterogeneity might benefit or simplify or facilitate evolution, with which mechanisms, where has it occurred, what are the effects, and so on. I mean, that this would be, it's a greater enterprise, and it's more, let's say, like an invitation or an open question. But also in the projects that the lab is working with, I can imagine that might be interesting to study different types of heterogeneity, like, for example, in neural dynamics. With some students, we are starting to explore different types of heterogeneity in realistic models of neural networks, and also from the group of Wolf-Singer in Germany. They found out that if they introduce heterogeneity in their artificial neural networks, then they were classified much better. And it seems that this general understanding that heterogeneity can increase the variety of a system that's linked to Ashby's law of requisite variety, it seems to me like a general explanation for why this is the case. But then I think we're still missing like a systematic understanding of what would be the precise heterogeneity that should be used in different situations. So just to conclude, most models of complex systems that have been studied are homogeneous, and we have seen that in many cases, heterogeneity gives criticality for free. So if we want criticality, it makes sense to take advantage of heterogeneity, because then we don't need to search too much in the parameter space to find that type of dynamics. And also, it would be interesting to explore heterogeneous versions of different models. The question of understanding better optimal heterogeneity is open. And once we understand that, then we could develop algorithms that would adapt the heterogeneity of systems to their current situation so that they perform better. Yeah, so if you have any questions, I just invite you to subscribe to Complexity Digest, which we edit already for some years, and then you can find the latest news and papers about complex systems.